So the second part of what we're going to talk about is what the line of correlation, the line of best fit does. So there's a couple different names for it. One of them is called the regression line, and it's also called the least squared line. Line of best fit, regression line, least squared line, or technically it is a trend line, and it's the best trend line, so sometimes people might say that. All right, so let's look at the characteristics, some three things that's true about the best trend line that we have. So it is the line that minimizes the sum of squared residuals. Next, this line of best fit contains the center of mass of the data. That is, it's called the point X bar Y bar, and of course we know that that means average, right? So in other words, it's the average value, the mean of the X's and the mean of the Y's. So add up all the X's and divide by however many there are, add up all the Y's, divide it, and that will be the center of mass. This is not necessarily a point of the data. It may or may not be data. It may be one datum. Remember, datum is just a singular data. So it may be. It doesn't have to be. It might be the data. Okay, next is that its slope and intercept can be computed directly from the given data. So you don't need a calculator to do it. You can just take the data and do it. However, it's so tedious that we rarely will do it by hand, okay? It takes a lot of adding and subtracting and multiplying and squaring, and it's not like the actual stuff is not complicated. It's just that there's so much of it. The process is complicated. Okay, so based on the line of regression we got before, we want to verify that the center of mass, which is given to us, 0.212 and $793.65 is on the line given to us. Well, of course, we know what our Y1 is from the previous page. So essentially, we're just going to plug that in to see if they are equal. And when I plug this into Y1, I do end up getting that. So I verified that it does indeed work. So after I plug it all into my calculator, I get 41,842.9. And that's the sum. Now, it's hard for us to tell how this helps because we haven't compared it to other potential lines. But if we did look at other lines besides this best one, the other ones would have a higher sum of squared residuals. So this one ends up being the best situation. All right, now we want to talk about correlation, and how it applies and how we can interpret, okay? So correlation ultimately has to do with how things fit in a line, okay? Line of best fit, how it fits in a line. Now, the sum of the squared residuals only says how my model fits. The sum of the squared has to do with any model, okay? Any model. So it could be a parabola. It could be an exponential function. It could be a decay function, whatever. So this just talks about the best fit for any model we're using. So that's why we use the sum of the squared residuals, because that applies to any and all situations. Correlation here is only about lines. How best does it make a line? So if we look at the data down here, we've got one data here that's perfect, a perfectly straight line, and it would have an R of a -1. So it's a perfect fit, but it has a negative relation. That is, as the X increases, the Y decreases. So over here is a perfect fit for as X increases, Y also increases perfectly. And a situation that describes this would be like the cost of a shirt, of course, right? So if I buy one shirt, it's $12. If I buy two shirts, it's $24. If I buy three shirts, it's $36. So that's going to be a perfect line because it's dealing with money. Gravity, which wouldn't be about a line, but And physics will end up being more scattered, something like this. So notice that we have the data is generally going in this direction, okay? So it's going to have a slightly lower R value, slightly lower R value. So here we call that a strong relation, a strong correlation. So this is a perfect correlation, like a negative 0.7 or a 0.8. Those are going to be strong correlations. But then when we get under that, we get into weak correlations. And lastly, there's no correlation. So let's just see what it looks like on a graph. If stuff were in this territory, like very close to zero, you would say that there is no correlation. So that territory would be no correlation. Then we've got some territory here. It would be sort of like a weak correlation. So somewhere about here would be weak correlation, as would this region over here be weak correlation. And then lastly, there is strong correlation and then a perfect correlation. So this region is strong correlation. And notice that we're going to go with strong and pay attention to whether it's a negative or a positive number, because over on the left here, it's strong, but it's going to be a negative correlation. That is, as X increases, Y decreases. Over here would be strong with a positive. And then in here would be weak positive, and over here is weak negative. So the correlation coefficient for the regression line that we just calculated, if we recall, was 0.9912, which, as we can see, is a very high correlation. So the description of that would be very strong positive. Very strong positive. All right, so let's interpret this one. So real quick, line of best fit. After I entered into L1, L2, I found this. The correlation coefficient is a strong negative correlation. And how to interpret the slope? What we say is, which is this part here, for every 1,000 pounds added to a vehicle, or not to a vehicle, but to vehicles in general, the MPG decreases by 4.2 miles per gallon. So the correlation coefficient R provides a mathematical measure of its linearity. Let me spell that for you. Linearity. That is how much of a line the data is, or how close to a line it is. But it does not provide any information about causation. It doesn't say one causes the other. So this website has some really good, funny connections between things. So we'll walk through that. Feel free to scan it or click on that to check it out. So.